Okay. So I welcome everybody. I hope everybody knows by now that the live streaming links are available on my channel on YouTube. So I don't think I need to post them anymore. So today is 14. Okay. All right. So in yesterday's class, we talked about relativistic velocity addition. Okay. Now let's see what our schedule looks like. We have today's class, we have tomorrow's class, and then I think I'll probably take one extra class on Friday. Okay. So today I'll start talking about relativistic momentum. Then I'll talk about relativistic energy, and that will cover our relativity portion. And we'll also do some problems along the way. Okay. But before I begin, are there any questions about the material that we have covered so far? Any questions? Okay, all right. So let's talk about momentum. So we have talked about position, we have talked about time, we have talked about position, we have talked about velocity, right? So the next quantity, the next physical quantity you talk about, right, is momentum and energy, right? So energy, momentum. Now, what is momentum, right? Where does the idea for momentum come from? So if you go back to one of my earliest classes, I had explained that so momentum is required in order to be able to talk about how the state of motion of any object changes, right? So what momentum does is it quantifies the state of force. We say that the state of motion remains the same, which is equivalent to saying that the momentum doesn't change. And if you have a composite system, that means you have more than one particle in the system, then the total momentum of the system doesn't change in the absence of an external force. And the total momentum can be expressed as the sum of the individual momenta, right? So they are vectors. So you can write the sum of these two vectors. Now, then we have this concept of energy. And where does this concept come from? So I had shown you the derivation, right? The work energy relationship. All right. So again, we want to talk about how much energy is work is done or energy is expended in changing the state of motion, right? So the first thing Newton's second law tells us, is the state of motion changing or not changing, right? So if dp by dt is not zero, that means the state of motion is changing. Then the second thing is we want to determine how much effort does it take to change the state of motion, right? So if you have a heavy object, it will take more effort, right? If you have a light object, it will take less effort. Keeping both of them at the same, assuming that you're changing the velocity by the same amount. So now you would expect that the amount of effort required to change the state of motion of an object would depend on the external force that is applied, right? So the greater the external force, the greater the amount of effort that you are applying on the system, right? And now, in the context of these point particles, we have when we talk about the state of motion, we say it's moving, right? And when we say change in the state of motion, we say, well, the position of the particle changes by some amount, delta x, right? When f is non-zero. YouTube, sir, by YouTube, that's what I'm saying. Now YouTube, everybody knows how to get my YouTube. No?
So it's not showing any live lecture.
Oh, is it not? Oh, my apologies. Yeah, for some reason there's been some issue, but 4 people are already watching, so that means that Pratyush, Charan, that means that other people are able to see the link. Anyways, I'll post it on Telegram also. Some people might not have it. Okay, so it makes it is a reasonable assumption that the effort that is required should depend on the force, and it should depend on, well, over how much time that force acts, right? Or over how much distance that force acts, right? And then there is also the question, well, you can have a force which acts in a direction perpendicular to the displacement of an object, right? So which of these components of the I sent in Tele, which of the components of the force should contribute to the effort, right? And well, again, we know this is from empirical evidence, right, that if you have a force that is in the in direction of motion, that will cause a change, that will require an effort, right? That will require some external work to be done by an external agency. And the reason we know this is because, for example, you can consider the case of circular motion. Now, if you consider circular motion, you have a particle that is attached with some string, let's say, and it is moving in a circle, right? Now, when it moves in this circle, it experiences a force. It experiences an acceleration, first of all, and it experiences a force. These are 2 of the most non-intuitive things when you first learn about classical mechanics. At least they were for me. Because I was like, well, there is no acceleration. The body is moving at the same speed. But the whole point is that the speed is not important, right? The velocity is important, the direction. And the direction of the velocity keeps changing. So there must be a force which is acting to change that direction. So you would think, well, some work, that force must be doing some work on the object, right? But from conservation of angular momentum, right? Conservation of angular momentum is a consequence of Newton's laws of motion. What is angular momentum? Angular momentum is r cross p, right? So if there is no external force, then angular momentum is also conserved. So if there is no external, Babu, hi. Okay, now go. 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 कैसी जाओ? हाँ बंद करना मम्मी. So for an object in uniform circular motion, there is no external torque that is required to keep it in the uniform circular motion, right? So that means there is no work that is being done. There is a radial force, but it is not doing any work, right? Even though there is a displacement enough. So from such considerations, right, it follows that it is the direction parallel to the force that contributes. So the expression that one makes a guess, okay, so this is also a guess, right, is that it should be f dot dx, okay. And then, so we write down what this dw is, then we do a little bit of algebra, right? We write f as dp dt, we move some of the differentials around, and we can write the whole thing as this p dot dp by m. And when you integrate p dot dp, you get p square by 2m. So this is what tells you that you can associate with the state of motion of an object a quantity which is given by p square by 2m. And that changes in this quantity measure the external amount of effort required to change the state of motion. Right? So similarly, what we want now, right, is we want a notion of momentum first of all, and then a notion of work. So, but in a relativistic context, okay. So what we have seen that, well, everything is modified, right? Velocity is modified, positions are modified. So it makes sense that the notion of momentum should also be modified in some way, right? So let's ask what possible modification there might be, okay? So again, I have some, let me just make this y instead. I have some frame of reference. In this frame of reference, there is a particle which is moving at a velocity v, okay? And this frame of reference is moving with respect to an external observer with some velocity v naught in the x direction. And the external observer is somebody here, x prime, y prime, right? So now we want to ask what is the momentum of this particle, right? So again, the momentum of the particle, just like the velocity, just like the position and the coordinates and the energy, will depend on the frame of reference. It will depend on who is observing the system, right? Which observer is looking at it. And again, I just want to emphasize that when I say observer, observer doesn't have to be any conscious entity or anything like that, okay? It is just a frame of reference is just that. Okay. And forgive me, I have to take my Digene tablets again because it's that time of the day when I start getting acidity. So, sorry about this. It might seem like I'm having some peanuts in the middle of a class. That's not a very professional thing to do. So we assign a momentum, right? So let's first look at the Galilean notion. We assign a momentum P is equal to mv. This is as seen by the observer O, right? So what is the momentum of the object as seen by O prime? It will be P prime, right? And what will P prime be? Well, P prime will be natural to think that it will be some m times v prime, where v prime is the velocity of the object as seen by O prime. And what is this v prime? Well, this is just going to be m times v plus v naught. right? According to the Galilean velocity addition. Okay. So now let's try this with the relativistic velocity addition. So let us first make a guess that when I talk about relativity, okay, now you might think that, well, why don't I just define P as mv? Okay, and then what will P prime be? Right, it will be this, right? M times B prime. But I know that this will be M times V plus V naught over 1 plus V dot V naught by C square. This, by the way, is the general vector expression for velocity addition, I think. Does this take into account all of the aspects? Okay, so I'll just be careful again and just assume that everything is in the x direction. So we'll just write P prime is mv x prime, that's m times vx plus v naught over 1 plus vx v naught by c. Okay, so for simplicity I'm just taking the y component, but you can have an x component also. So let's see what will be the y component. That will be m times vy prime, and what will vy prime be? Well, it will be m times vy over gamma into 1 plus vx v naught by c square. And the same thing for pz prime, it will be m times pz, vz prime, right? So these are the relations for, this is what the momentum of the particle will be as seen from the frame of reference O prime, right? Okay. But now our definition of momentum, whatever it is, it should satisfy some, there should be some consistency requirement, right? So what should be a consistency requirement? Well, in classical non-relativistic mechanics, right, we have this very important principle of conservation of momentum and also energy, right? So the natural question to ask is, well, shouldn't momentum be conserved for special relativity, in special relativity, right? So now the thing is that in special relativity, right, our relationships between coordinates of different observers is modified, right? But that doesn't mean that momentum and energy can suddenly be created and destroyed out of nowhere, right? I mean, we want to maintain that as a principle of physics. Otherwise, you know, we will lose the ability to keep track of anything, right? So if you have some energy or some work, it should come from somewhere and it should go into something, right? It cannot just be created out of nothing and go into nothing. So momentum, we require conservation of momentum and energy in special relativity also. Okay, so we take this as a basic guiding principle. Now we can ask the question that if I define momentum in this way, if I define the momentum as P is equal to mv, okay, and then I write down this momentum, okay, do I first of all get is momentum conserved? Okay, but before that there is one other thing actually, which is the following. So let me copy these relationships to the next page. So I go from O to O prime, right? I perform this Lorentz transformation to go from O prime, and P is equal to mv goes to P prime is equal to mv prime, where the components of P prime are related to these components in this way, right? And so this I can write as P of x plus mv naught. I'll write that as P naught, 1 plus Vx V naught by C square. This I can write as Py over gamma 1 plus. And this I can write as Pz, so no prime, right? Right, I'm just taking this, I'm writing everything in terms of momentum only. Okay, now, so now I can perform the inverse Lorentz transformation, right? I can go from the perspective of O prime back to O, right? So if I perform the inverse Lorentz transformation, what should happen? P prime is equal to mv prime. Okay, whatever this quantity is. When I perform the inverse Lorentz transformation, I get some momentum. I'll call this P2 mv2. Okay, so I start with my original particle in the O frame. I perform a Lorentz transformation to the O prime frame. In the O prime frame, the momentum becomes this quantity, right? Then I perform an inverse Lorentz transformation. When I perform the inverse Lorentz transformation, I go from the O prime frame back to the O frame, and then the momentum becomes this quantity. So instead of 2, I can put 2 primes. Let me put 2 primes, mv double prime, right? So I can say that I'm going from O prime to O double prime, but O prime and O double prime and O are the same. Now one can ask the question, is P prime is double prime equal to P? Right? Makes sense, right? It should be the case, right? So we can ask if that is the question. So we just have to apply this transformation again, but with a minus V naught sign everywhere. To which momentum? To this momentum, right? So what is Px double prime? Px double prime, if I apply the same transformation, right, is equal to mvx double prime. Mvx double prime will be m times Vx prime minus V naught, right? That's the inverse Lorentz transformation, divided by 1 minus Vx prime V naught by C square, right? Now, what should this be equal to? This should be equal to mvx, right? But it's not going to be equal to mvx, right? Because if you substitute the expression for vx prime in this, let's substitute the expression for vx prime. Vx prime is Vx plus V naught, 1 plus Vx V naught by C square. Right? So just take a second to understand what is happening. I'm performing two Lorentz transformations from O to O prime and from O prime to O double prime. Okay. But the transformation to O double prime is just the inverse. Right? So if I just perform the inverse, I should get back the same quantity, right? It should not change, right? So then I am just following this procedure. So I calculated the momentum after the first Lorentz transformation. Now I'm calculating the momentum after the second Lorentz. But Vx prime, I remember, can be written in terms of this velocity addition formula, right? So now I substitute this expression back in here. So I have Vx prime minus V naught in the numerator, which becomes Vx plus V naught, 1 plus Vx V naught by C square minus V naught. Okay. What is this equal to? This gives me, when I multiply the denominators out, I'll get Vx, V naught will cancel, plus, Vx minus Vx times V naught square by C square divided by 1 plus Vx V naught by C square. Right? This is the denominator, this Vx prime minus V naught. Okay. Now let me look at this thing. Sorry, this is the numerator. So let me look at the denominator. What happens to the denominator? So this expression, by the way, can be simplified and we can write it as Vx times 1 minus V naught square by C square. Okay. So now what about the denominator? So let me color code everything so that sort of like matches, and then you can perhaps look at it a little bit more. V naught by C square is equal to, so this is the green part. Right? So this is what? This is equal to 1 minus, now I substitute this expression for Vx prime. Vx plus V naught, 1 plus Vx V naught by C square. Right? Times V naught by C square. I'll just move this a little bit lower so that there is, well, maybe put here and take this and put it on here. Okay, yeah, I think maybe this is a little bit better. Right? So again, I can do the same thing. So I multiply everything out, divide, and so on and so forth. What will happen? Let me see. Some little bit of algebra. C square. I'll get C square plus Vx V naught minus Vx V naught plus V naught square. Okay, divided by C square times Vx V naught by C square. What will happen? This will cancel out, right? And I will get C square. Again, I can write this as 1 minus V naught square by C square divided by 1 plus Vx V naught by C square. Okay. So now I can take this numerator and denominator and I can divide them. Right? And when I divide them, what will happen? Well, this factor of 1 minus V naught square by C square will cancel. This factor of 1 plus Vx by V naught times V naught by C square will cancel. And what will I get? I will be left with, when I do this calculation, Px is equal to Mvx prime double prime. It will turn out to be equal to Mvx. Okay. So, okay, fine. This would suggest that this definition is okay, right? But then I have a second consistency check. So this is one consistency check, okay? Then I have a second consistency check. What is that? That is conservation of momentum. So how do I do that? I have to look at the collision between particles. So I imagine that I have one particle with momentum P1, another particle with momentum P2, okay? And this is again all in some frame of reference. And this is V naught. This is O prime, okay? So now I can ask the question, what happens? Is momentum conserved as seen by O prime in this collision between particles or not? Okay. Now I am not going to go into the details of the calculation because it's a little bit involved. Okay. But what happens is that if you do the calculation, if you ask, is momentum conserved? So what does that mean? So the initial momentum, let's write that as P, capital P, is P1 plus P2 as seen by O, right? The same momentum as seen by O prime will be some P1 prime plus P2 prime. Okay. Now, one can ask, so after the collision, what will happen? Now we take a certain special case. We take both the particles to be of the same mass and to have the same speed, only the direction is different. So you said P1 is equal to mv1 and you said P2 is equal to minus P. Okay. And now what is the total momentum? The total momentum is 0, right? P1 plus P2 is 0. So what about this? What happens from the perspective of this guy, right? So then you pick V naught, your relative motion. You pick this to be equal to V1. So what does this observer see? So this is a particle moving with velocity V1. This is a particle moving with velocity V2 as seen by O. And now I take O prime. With respect to O prime, the whole, so I'll take this velocity to be moving in the opposite direction actually. And I will say that this is minus V1. So O is moving in the negative direction with respect to O prime with this velocity. Now, what is the momentum? What is the velocity of the first particle as seen by O prime? V1 prime is 0, right? And V2 prime will be, you will have to add the velocities. So minus V1. Again, since we are all only dealing with the X component, V2 X prime, I'll just write V2 X prime is equal to minus v1x plus v2x. Okay. So you set up this kind of a situation, okay, and then there is a little bit. There are a few other steps. So I'm again, it becomes a little involved, right? The computation is a little complicated. So I will share the notes with you all, okay? But the end result is that momentum is not conserved. That means when you consider this kind of a collision, momentum is not conserved in the as seen by O prime. Okay. So that means that this P is equal to mv. This definition is not a good definition for the relativistic case. One second. Okay, so now what is the correct expression for momentum? The correct expression turns out to be P is equal to gamma mv. Well, what is gamma? Gamma is equal to 1 over 1 root of 1 minus v square by c square. Okay. So I know that like not giving a what do you call it, proper derivation of this is not a satisfactory state of affairs, but I will give you a reference where you can find a proper derivation. That is in the Feynman lectures on physics, volume 1. I believe it's volume 1. Okay, that is one place where you can find a derivation of this expression. So what happens with this expression? Now again, I have some x and y and some O, some object with some velocity v, with some component vx and vy, and then the whole frame of reference is moving with some speed v naught with respect to O prime. All right. So one asks, what happens to the momentum? How is the momentum defined according to this equation? So the momentum as seen by O is going to be gamma mv. Now what is this gamma? Gamma is equal to root of 1 minus v square by c square. Now the question is, which gamma is this? This is not the gamma of the relative motion. So there is some relative motion between O and O prime, right? But we have not done the Lorentz transformation to O prime yet. We are only looking at O. Okay. So this gamma is the gamma of this particle. Okay. So actually there is one way to sort of like heuristically think of this derivation, is that we think of this momentum as m times dv dt, right? So if you want to consider the perspective of the observer who is moving, right? Then what should happen is that this time component should become dilated. So if you take into account the time dilation, then so this would be the definition of the momentum in the rest frame of the particle. So if you are in the particle's rest frame, this would be the definition, okay? But in the particle's rest frame, what is the velocity? The velocity is just zero, right? Right. So in its own rest frame, any particle has zero momentum, right? In your own rest frame, you have zero momentum. So let's just say this is the rest frame definition, right? We want to work with the definition, even though it's zero, okay?
Excuse me, sir.
Yeah.
Sir, how is it m dv by dt? The momentum.
Oh, my bad. My bad. Dx.
Okay.
Now we want to look at this from the perspective of an observer with respect to whom this particle is actually moving, right? That means this particle is now it's moving with some velocity v. So let me write this as p of x, and there will be p of y, m dy by dt. Okay. So this is zero, but we ask, well, what happens if you go to a frame of reference in which the observer is moving, let's say, in the x direction? So the particle then appears to move in the same direction. So how should you define this quantity? dx prime by dt prime, right? And now what is the relation between dt prime and dt? Dt prime is equal to so this is the time interval. So I would write dt is equal to gamma dt prime. So I would write dt prime is equal to dt by gamma. So this px prime would become equal to gamma m dx prime by dt by dt. And what about this dx prime? Now you would say, well, this wouldn't this dx prime undergo some length contraction? But the thing is, see, in the rest frame, the particle was not moving at all, right? So when it is moving, when we go to this other frame of reference, when the particle picks up some motion, right? There is no Lorentz transformation involved for the position. What changes is the time interval, not the position. So one way of thinking of this is that remember that every particle or every system carries a clock with it. Right? There is a clock with everything. So if you have a muon, it is carrying its own clock. Right? And if I define the momentum as this thing, dx dt, right? And I'm saying this is the definition of the momentum in the system's own frame of reference. Now, in the system's own frame of reference, this momentum, the value is zero. Okay? The value is zero, but I can still use it as a formal definition. Okay? And then I can ask, right? I go to a different frame of reference. with respect to that frame of reference, now my particle is actually moving. It has some displacement dx and dy, dz, whatever. Okay. So with respect to that moving frame, what happens? This is the time interval in the rest frame of the particle. This is the time interval in the rest frame of the observer. And what is the relation between the two? dt is equal to gamma dt prime. Right? So if 1 second elapses in my rest frame, 1 times gamma seconds elapses in the moving frame. So dt prime is dt by gamma, and that gives me this expression. But what about you? Again, you will say, what about dx? Well, dx is simply measured with respect to this observer, right? So we are not really measuring dx with respect to this observer's frame of reference. So anyways, this is not such a rigorous derivation, but this I will leave it at this. Okay. So I will come back now. Let me come back to the question of how to define the momentum for one. What is the consequence of this definition? So let me again take this particle to be moving like this, the frame of reference to be moving like this with respect to O prime. So what is the momentum now? Px is equal to mvx times gamma, which is root of 1 minus vx squared by c squared. Okay. Now what is this momentum as seen by O prime? It's equal to gamma prime mvx prime. Now what is gamma prime? Gamma prime is equal to 1 minus vx prime squared by c squared. And what is vx prime? Vx prime is equal to vx plus v naught over 1 plus vx v naught by c squared. Okay. So this becomes a complicated expression when you plug it back in here. So the point again is that, so let's say that you have a second particle, okay? And you have a second particle that is, let's say, moving in the y direction with some speed vy. Then again, I can ask, what is py for the second particle? Py prime, right? It would be mvy prime divided by which gamma? 1 minus vy prime squared by c squared. Right? So this is for a second particle. So let me call this particle A, let me call this particle B. So this is all for particle A, this is for particle B. But if you have only one particle, then of course your gamma will just be 1 minus v square by c square. Right? So if I have two particles, one is moving with some velocity v1, another is moving with some velocity v2, I would write p1 is equal to gamma 1 mv1 and p2 is equal to gamma 2 mv2. What is gamma 1? Gamma 1 is 1 over root of 1 minus v1 square by c square. Gamma 2 is 1 over root of 1 minus v2 square by. Okay. Now, is it possible for me to take another 15 minutes?
Yes, sir.
Okay. I mean, you all, when is your next class?
We
Tomorrow,
don't have a
sir.
class.
You don't have a class. Okay.
No class.
Well, you might be hungry, but I'm also hungry. So, okay. Given that we are all hungry, I just want to, okay, no, never mind. I'll stop here for today. This is enough. Okay. I was just trying to rush because I'm like thinking, okay, well, I have to cover the syllabus fully, otherwise, blah, blah, blah. Durghatna se der bhali. That is in saying in Hindi, right? It means better to go slowly rather than to have an accident. Or haste makes waste. Okay. So this is the momentum of these particles in this frame of reference. When you go to a different frame of reference, what will happen? V1 prime and gamma 1 prime, gamma 2 prime and V2 prime, these will all change. So the calculations with momentum become very, very involved. Okay. But we will be doing those calculations in one of the following classes. So again, as I said, yeah, so this is the bottom line. This is the relativistic momentum. Now, one aspect of this relativistic momentum again is that when the speed is much less than c, it will become approximately the same as mv, right? So that is again a consistency check. At the limit of low velocities, your expression should become the same as the non-relativistic one. Okay. And again, for those who are curious to see the derivation, I can recommend the Feynman lectures on physics. Okay. But it's not a very simple derivation, so I haven't included it in today's lecture. All right, so I'll stop here.